All right, we're going to pick up with this section called the activity series. Now, for those following along in your book, this is still chapter 4, section 4, which is oxidation-reduction reactions. So we're still on oxidation-reduction reactions. Keep that in mind. We concluded our last session by talking about the propensity of metals to give up electrons. It's a property shared by all metals. We talked about where metals are located on the periodic table, where nonmetals. And then we had this unique reaction where one metal, neutral metal, meaning a metal with its full contingent of electrons, is giving up some of those electrons to a metal cation, i.e. a metal that is deficient of electrons. All right? And then we said, well, why is that so? What is about one metal cation that says, I want the electrons more than you do? Okay, well, that's where we come up with this activity series. Here's a table. Now, there's a larger table than this in your book, but this is a nice summary. And we talk about activity in terms of the ability, or should I say the propensity, of a neutral metal to say, here, take my electrons. So you'll notice there's a series of reactions here, and they're all oxidation reactions, meaning what oxidation is something losing electrons. So let's look at this top one. Lithium neutral metal loses an electron and creates a lithium cation. And you'll notice all the reactions top to bottom are oxidation reactions. The topmost metal is the most active. And this is in aqueous solution. There's other ways to measure this, but let's just say for aqueous solutions, this is all we care about. Lithium, the most active metal, meaning of all the metals on this side, that's the one that's going to just blast out its electrons. All right. Now let me say something a little bit about the topmost elements. You'll notice lithium, potassium, barium, calcium, sodium, magnesium, those are all group 1 and group 2 metals. Remember the alkali metals and the alkaline earth metals. If you look at the periodic table, okay, we said metals are on the left side, predominantly all elements of metals. Non-metals are on this side. As you move from right to left, and actually from bottom to top, the metals become more active, meaning they are more willing to give up those electrons. So again, if you look at this series, these series of metals, they're up in this part of the periodic table. Okay. Now, how do we match these two up? We're talking about one metal giving up electrons to another metal cation. I suggest you use what I call the diagonal rule. Very simple. Looking at the activity series, it states that any metal, neutral metal on the left side, so you notice all these metals here are neutral metals, will give up an electron or maybe 2 electrons to a metal cation on the right-hand side as long as that's one row or below. What does that mean? That means lithium metal will give up electrons to potassium cation, barium cation, calcium, any of these on this side. It's the most active metal. Okay, pick out another pair. Aluminum. Aluminum will give up electrons to manganese +2 and anything on this side. It will not give up electrons to magnesium +2, sodium, and so forth. All right, that's what's meant by the diagonal rule. Okay, so using the activity series, you ought to be able to predict what can happen when you've got one metal cation and a neutral metal. So here's an example. On the left side, we have a copper 2+ solution, hence the blue color, with a zinc metal strip just floating there. Okay. On the right side, we've got the zinc 2+ solution, so aqueous zinc metal cations. Remember, right, that is zinc 2+ AQ, and this would be copper 2+ AQ. With a copper strip. So the question is, does the copper give up electrons to the zinc, or does the zinc give up electrons to the copper? Well, let's look again at this. So here are the two potential reactions that I've outlined for you. Notice zinc metal giving up electrons to copper 2+. Let's write that better. Or copper giving up one or more electrons to zinc 2+, and then here would be the potential products. All right. So here's a a segment of the table where we can judge it. So let's use a diagonal rule. Let's pick out zinc and copper. Well, here's the zinc, and copper's down at the bottom. So by a diagonal rule, that means the zinc metal will give up its electrons to the copper 2+, meaning that you do not have copper solid plus zinc 2+ going anywhere. Right? It means copper wants those electrons. Once it's got them, it's going to hold on to them in the presence of the zinc 2+. All right. So this is what you would find. If you look closely at the zinc strip, it starts to look fuzzy. And why is that? Well, it's because the copper solid is plating out, copper plating on the zinc. And here's the reaction right here. At a microscopic atomic level, this is what we can represent. These are zinc atoms, neutral atoms in the strip, and then they are giving up electrons to the soluble copper 2+, which then stick onto the zinc strip, shown by this red sphere, and that's what gives this fuzzy growing mass appearance. So what we say is actually the zinc strip gains mass, and the mass it's gaining is from the copper metal plating out. Okay, so once again, we say zinc metal will be oxidized by the copper cation, and here's the net reaction, right? We can leave out, what is our spectator ion? Spectator ion is a nitrate, and minus AQ, and that's going to be on both sides, AQ, so we cross those out. And you'll notice the net reaction, zinc metal giving up electrons to copper 2+, plating out copper solid. Now, one thing I want to point out too is, when we look at the table, there's zinc, there's copper. The zinc reaction is going as shown from left to right. I'll write that with this big bold arrow. But the copper reaction is actually going in reverse, meaning copper 2+ is being reduced. And that hence we show the arrow going from right to left. Just think of it this way. These electrons from the zinc are serving as the reactant on that reaction. All right. What about, we also talked about another potential reaction. That is a metal reacting with the hydrogen cation, right? So we said neutral metal, I'll put that as M solid, plus H plus AQ, okay? And what we had is potential for hydrogen gas plus the metal cation, I'll say plus NAQ. Well, how do we judge what's going on there? And by the way, I also mentioned that this H plus can come from water. So if you've got a really active metal like sodium lithium, they want to give up electrons so much, water will serve as a sufficient source of the H plus. For other metals, you need a stronger amount of acid, in other words, a larger amount of H plus, and that requires an acid. Well, look at the activity series. We've got hydrogen in there, and notice the reaction. It shows hydrogen gas being oxidized to give up electrons and produce H+. The diagonal rule still fits here. What does that mean? That means any of these metals on this side, okay, will give up its electrons to the H+. So any of the metals above the hydrogen line, the neutral metals in the presence of an acid will give up and create the hydrogen gas. So again, this reaction is going to be going from right to left. All right. So here's the question. Which of those metals, silver or iron? Well, here's iron, and here's silver, okay? Well, you can see that iron is the only one that would give up its electrons to H+ by the diagonal rule. Silver is not. It's interesting to note that silver, copper, gold is also down here. All the metals that you associate with being precious metals that we've used throughout the eons because they do not oxidize easily, especially gold, are down below, meaning they're not very active, which is why we can use them as precious metals. Okay, so I'll conclude by saying this. You should be able to predict any of these reactions given the activity series, and you'll be given that for your exam, so don't worry about that. You don't have to memorize them. You should know, again, just to remind you, that in terms of the periodic table, metal activity increases in this trend, and we'll talk about periodic trends later. Okay, but again, given any two potential reactions and the activity series, you ought to be able to predict this. So I conclude with giving you this: zinc in a magnesium 2+ solution or magnesium in a zinc 2+ solution. Look at your activity series and tell me which way it's going to work.